cost to those institutions, which usually have a fixed type of income. So in a context of this urgent need to limit global warming to the 1.5 degree threshold by 2050, we need to come up with new approaches, new methodologies to reduce our energy consumptions, starting with buildings, and more particularly university buildings. New approaches, one of them is the digital twin technology. So what is a digital twin? It is a virtual model aiming at representing the operations and system configurations of a building physical object. So we're basically just taking a building in its real life conditions and creating a virtual model of it, encompassing all of the aspects of the building itself. With a digital twin, you can then run building energy simulations. And with those simulations, you can not only identify potential energy performance gaps in your building, but also test out energy efficiency measures virtually before implementing any major changes in your building. Performance gaps, just a bit more details on what those are. Energy performance gaps are the difference in energy consumption between your actual building right now, years after it's been constructed, and the initial energy consumption estimates that were done during the design or construction phase. So usually these two energy consumption values differ because some equipment may have failed over time, but also potential misunderstanding of how the building was going to be used, how occupants were going to behave inside this building, because let's remember that it's not the building that consumes energy, but the people inside the building. So these account for the energy performance gaps. So for me, as part of my dissertation, the goal was to demonstrate how digital twin technology was a great tool to assess the energy performance of buildings. And for this, I took the case study of the Andrew Wiles Building here in Oxford. It's the home to the Mathematical Institute for the university. It's quite a recent modern building. It was built in 2013. So it's 10 years old now. It houses over 900 undergraduate research students and 500 staff and researchers. It's a big L-shaped building with two main wings. In each wing, you have those big atria spaces with roofs fully covered in windows to maximize daylight. It is also modern in a sense that all the HVAC configurations are monitored on the building management system. Each room is equipped with a thermostat. Let's also note that the building the heating is mainly provided by ground source heat pumps, so electricity based, with gas boilers acting as backup heating sources, and it has a mechanical ventilation system just to distribute fresh air across the building. These are important details for later on. Why did I choose this building as a case study? Well, I was able to retrieve the energy performance certificate of the building before it was constructed and the energy certificate of the building from last year. From the certificate that was done before it was constructed, you can see, so basically this is energy consumption estimate that was done before the building was built, and with a quick back of the envelope calculation, this score corresponds to roughly 30.5 kilograms of CO2 per meter squared per year of emissions solely associated to the energy consumption of the building. And the display energy certificate from 2022, so this is a mandatory certificate that every building needs to have renewed every year, and it's based on the actual energy consumption of the building from the year before. Again, back of the envelope calculation leads to roughly 45 kilograms of CO2 per meter squared per year. So emissions, again, solely associated to the energy consumption of the building. So you see a difference between these two numbers. This is the energy performance gaps that I was referring to. It's right now the building is roughly consuming 30% more energy than what was initially planned. So the objective was to identify what were the causes of this difference. And to do so, I created two different digital twins. The first was aiming to represent the building as it was initially constructed, using initial intended operation documentation, and a second model aiming at reflecting the real-life condition of the building right now. I mean, that was last year, so in 2022. And the way I created the model was basically by calibrating it with the actual meter consumption of the building to have a model that could best reflect the real-life operations of the building. I ran monthly energy simulations using the software Design Builder, which is the graphical user interface for Energy Plus. Energy Plus is a very powerful tool for building energy simulations. And with this, comparing those two models, I was able to quantify the potential energy savings that could be achieved if the identify equipment failures and controls were further investigated. Starting with the as-built digital twin configuration. So this one aims at reflecting, as I said, the initially intended operation of the building. This is a 3D model of the building that was provided by the architectural firm responsible for the project development. I imported this model into Design Builder. It has over 400 zones. It's a very, very detailed model to maximize accuracy in the simulation results. And I was lucky enough to have access to a large database of documentation from the construction phase of the building with very detailed lighting schedule, equipment information, data sheets, commissioning reports. So this is, for example, the complete heating circuit with every single component. So this was a very rich resource and database from Estates Services, which allowed me to create a very comprehensive as-built DT configuration. Something also that is very important in the twin is occupancy, because again, people consume the energy, so you need to model those people as accurately as possible. For this, I used card entrance data, which allowed me to adopt a clustering approach to my occupancy patterns. So I identified 4 main clusters of occupancy rates: term time, out of term, summer, and winter holiday. With this, alongside using room booking systems, on-site serving, I was able to derive typical occupancy profiles for weekday and weekend for each room of the building, which I then imported into my Design Builder model. I use the same occupancy profile for the as-built and operational DT configuration to be able to isolate the impact of equipment failures in my simulation results. Speaking of the operational DT configuration, as I said, the way I calibrated this model was using the metered electricity consumption. The Andrew Wiles Building is quite modern in a sense that it has 4 submeters per floor, each metering power on one side and lighting. So very high level of disaggregation in the metering data, which allowed me to clearly identify the energy consumption of each energy service provided. So heating, cooling, ventilation, lighting, and unregulated loads, which is everything like computers, kitchen equipment, and whatnot. And as part of this operational DT configuration, a second important step was to identify the current control and equipment failures to implement those into my model. So after talking with the building staff, but also estate services and on-site serving, we noticed that some photocell sensors were not functioning properly. So these sensors were installed in the large atria with the roof windows, and they were supposed to dim the light when there was enough sunlight, but these were not working anymore, so the lights were remaining on, although sunlight was enough to illuminate the spaces. The VAV boxes, so variable air volume boxes, these are the boxes that are used to distribute fresh air across the building. Some of them were shut down, so this required mechanical ventilation to be pumped more to provide the same amount of fresh air to the building. On the metering data, it was also noticed that the heating water pumps were still operating during summer when heating was not required, so this incurred an additional electricity consumption. And finally, the building is equipped with shading panels that slide to provide shading during summer, and those panels are supposed to slide via a motor that was not working anymore, so no shading was provided anymore during summer. So these are all little failures that I modeled in my operational digital twin to see what the impacts were. And I calibrated this model using the metered electricity consumption to really reflect the current building as it is as best as possible. One challenge that I had to deal with is that the heating and cooling services of the Andrew Wiles Building are shared with the neighboring building. So I had to do a bit of approximations regarding my metering data and my model on these aspects. So moving on to simulation results, the two main energy savings that I was able to identify from the simulations were lighting and ventilation. So on each graph, you have the simulation ran over the whole year for each month. In green, you have the results from the as-built digital twin. Dark blue is the operational digital twin, so aiming at reflecting the current operations. And light blue, the metered consumption, so the real consumption of the building. Every time the dark blue and light blue, the goal was to make them as close as possible for calibration purposes. And as you can see, lighting, there's almost a 30% reduction in consumption comparing the as-built and operational. This is solely due to the photocell sensors not functioning properly. So this was my first recommendation, investigate those photocell sensors. Second recommendation was the variable air volume boxes. So for ventilation, we have almost a 50% reduction in electricity consumption if the variable air volume boxes are repaired. So that was my second recommendation. Lighting and ventilation combined together, if those equipment are further investigated, this could lead to an energy saving of 230 megawatt hour for the whole year, or almost 70,000 pounds for the whole year for the building. Moving on to heating and cooling, again, less opportunities for energy savings in that area, but we can still see the heating water pumps functioning during summer. This is additional energy consumption which could be avoided if they're shut down. For gas, so as I said, there are some gas boilers in the building that act as a backup heating source in times of peak heating demand. I had some large differences between my model and the metered consumption. This is because of the challenge that I mentioned, the difficulty of clearly identifying the split of heating services that were redirected to the neighboring building. So I left that on the side and did not quantify any energy savings on that side due to this uncertainty. And for cooling, you see the asphalt model being slightly lower. Again, this is due to the variable air volume boxes. So cooling provides, so the mechanical ventilation uses the cooling services to provide fresh air. So if your variable air volume boxes are not functioning properly, then your ground source heat pump will pump more for the same amount of fresh air. So here my recommendations were to investigate those heating water pumps, see if we can shut them down during summer, and also install an additional gas submeter in the building so that we can avoid all those uncertainties in the gas metering. Nevertheless, just looking at cooling, you can save up to 35 megawatt hour per year or 10,000 pounds per year by just, again, repairing the variable air volume boxes. And finally, the last thing I tested on my software design builder was the shading panels that I mentioned. So these are supposed to be able to slide to provide shading. None of them are currently working. They're all in open position right now. And I just modeled the warmest week of 2022. So this was during the heat wave. With and without the panels, on average in the offices, you can decrease your indoor temperature by 2 degrees daily, which is a very crucial result because heat waves like the one we faced in the UK in 2022, they're going to become more and more frequent, and zero energy solutions like simple shading systems are going to be crucial, especially that cooling demand is going to surge in the next, in the upcoming years. So digital twins are valuable tools in that sense that they can clearly show, demonstrate the benefits of those type of shading solutions. To conclude, the final step of my project was to compare with typical and good practice benchmarks of university buildings. So the building's actual electricity metered consumption was already below the typical practice. It's already a well-functioning building in that sense, but it was still higher than the good practice benchmark. And that's when the digital twin simulations came in handy, because with all the identified equipment failures and controls that we identified, we could have our building fall right below the good practice benchmark. Gas, it's a very separate, I just showed it here for visual purposes, but again, the meter consumption is already quite lower than the good practice and typical, just because gas is a backup heating source, so it's not the primary heating source for the building. My final recommendation that I brought up to the building management staff at Andrew Wiles Building were to investigate the photocell sensors, the variable air volume boxes, see if we can shut down the water heating pumps during summer, and investigate the failures associated to the shading panels. Overall, if all of those are further investigated, there's a potential of energy savings which are equivalent to £80,000 for the whole year. This is for only one building in the university. Oxford has hundreds of buildings, so I'll let you imagine the amount of money that could be saved if simple digital tools like this are used for our buildings. So to conclude, digital twin energy simulations are valuable to identify performance gaps in operational university buildings. This is a tool that building managers themselves could use to assess the performance of their own building and see how they could save on energy and money. There is, however, a trade-off between the accuracy of your simulation results and the input data that you get. I was lucky to have very comprehensive, detailed, disaggregated data for the building. This is not always the case, almost rarely the case. So now, as part of my DPhil, my goal is to identify the sensitivity of simulation results accuracy with respect to input data. So when you have less data or less accurate data or missing data, how do you go about this? Can you still get accurate simulation results? And a second part of my DPhil will focus on developing more user-friendly and accessible digital tools so that building managers could really use those tools themselves and not me with a full master's degree, anyway. Make them more user-friendly for everyone so that everyone can use them. Thank you, and let me know if you have any questions.
Really enjoyed that, very punchy, and there's some great savings to be made. Can I just ask a question about the role of the unregulated load? Because
yes.
My understanding is the energy performance certificate doesn't attempt to say how you're going to use the building.
Yes.
Whereas the display energy certificate just bears up all because it's
yes.
what did the bills tell you. So what's right. The role of that?
Sorry, I should have, I forgot to mention this. Yes, so in my back of the envelope calculation, what I did is that for the, just to summarize for everyone, the energy performance certificate that a building gets before it's constructed does not include any equipment that is plugged into the building, but the display energy certificate does. So what I did is that I took the 2022 unregulated load power consumption, equivalent CO2 emissions, and I added it just to have comparable units for my two numbers. Yeah. Again, very back of the envelope calculation, but it was the best way to have
it sounds like you could walk around the building and find some equipment that was left on as well and maybe find even more savings. But...
Maybe, exactly, yeah.
That was great, thank you very much. And yeah, I think it was good that you mentioned at the end how fortunate you were to have data that was forthcoming and high quality. That's really high risk theses. I was just wondering if you could say anything about how your work was received by the people at the Maths Institute and if they're taking action.
So I'm not sure if they are taking action, but it was very well received, not only from the Andrew Wiles Building, but also estate services. So I presented the results to both parties, and I think these are definitely issues that they will investigate. Timeline and actions, I'm not sure. I should follow up in a few months, maybe.
Keep looking out for those blinds.
Yeah, exactly.
Well, thanks for an interesting talk. And firstly, I'd like to apologize for being late. I might have caused some unwilling disturbance. But nevertheless, my question is regarding the future prospects of such model, which is very interesting to start with. Could you let us know a bit more about its predictive aspects, right? So things like, for example, say I want to change the orientation of certain heating equipment or cooling equipment, maybe change the materials of the building itself, how is that going to affect, for example, the energy model? Is this something that is going to be possible with such model?
Yes, definitely. So the software used and the approaches used is physics-based. So in the sense that it's highly modular. So all those details of playing around with equipment, envelope, fabric construction materials, all of this is possible on the model itself. And every time you can run a simulation and see how this affects your energy consumption. So this type of approach, so physics-based, software-based modeling makes this possible for
So in
sure.
other words, you are able to change parameters as such in order to...
Definitely, yeah.
In terms of occupancy, what did you find were there any key things you found with regard to how well understood you need the building to be from the point of view of how many people are in it at any one time?
That is a good question. Something I would have liked to do is compare this model with a less accurate model for occupancy. So I believe my occupancy modeling was very comprehensive and highly detailed. Maybe this was not necessary, and it would be interesting to quantify the difference in modeling errors if we took a more generic occupancy profile. So I am not sure actually.
Any other questions? No? Okay, well let's thank our speaker again. Right, okay, so our second speaker of the evening is Colin Kinghorn, who's going to be talking about the techno-economic optimisation of green hydrogen and green ammonia production in South Africa. Over to you, Colin.
Thank you very much. Yeah, apologies for the title, it's a bit of a mouthful. Yeah, this is my dissertation from the MSc in Energy Systems last year. Before that was at BCG for a couple of years, working primarily in the decarbonisation space. You won't be able to tell from these slides, apologies in advance. I'm now doing my second master's here at Oxford in something completely different, but I'm also running a startup in the sort of energy financing space. And we'll get onto that in this presentation, sort of the importance of financing and getting interest rates down when it comes to decarbonisation in the developing world. You know, this seems like a bit of a niche topic, and so I wanted to start by saying, you know, why is this relevant to the rest of the world, you know, when it comes to the green hydrogen and green ammonia play in Southern Africa. I think it's relevant for two reasons. First is, you know, in terms of providing a geopolitically reliable, low-cost source of green ammonia and hydrogen into the global market. I think Southern Africa is going to play a role there. So most research is pointing to Chile, South Africa, and Namibia forming kind of the second tier of globally competitive supply behind the likes of Australia, Saudi Arabia, and Morocco. This is largely because they have strong renewable energy cost potential. There's plenty of sort of low-cost land available, but the cost of capital tends to be a bit higher than you'd find in Australia or Saudi Arabia. You know, proof of this is if you look at RWE, for example, announcing a $9.7 billion green ammonia investment in Namibia. But now questions being raised about how do you sort of capture the value from that locally. The second reason why I think this is a relevant topic for everyone is that you know, many of the world's global powers are looking at Southern Africa and its decarbonisation as a potential blueprint for how we approach financing of decarbonisation around the world in other developing regions. So South Africa is the 14th highest emitting country in the world. It's arguably the most industrialized economy in sub-Saharan Africa, and it possesses significant hard-to-abate steel and chemicals assets where green hydrogen makes sense as a use case. And you know, there's significant consequences here if South Africa fails to decarbonize. 32% of export earnings at risk. Of course, the surrounding SADC region contains 4 of the 11 poorest countries on Earth, but also countries that are going to be critical for the supply of green technology minerals. For example, the DRC providing about 70% of the world's cobalt supply at the moment. So integrating that region into the green economy is critical. So, in terms of the literature, where were the gaps? Well, the green hydrogen commercialization strategy for South Africa is really the sort of governing document there at the moment, and it lacks specificity with regard to whether you transmit electricity over long distances, or wheel or pipe molecules as part of the green hydrogen ecosystem. Very little sort of in-depth analysis about which ports to prioritize for export. Almost nothing about how South Africa can collaborate with Namibia in this regard. And same thing in the literature, you find these kind of niche studies costing for specific use cases and looking specifically at production or at delivery, but very few integrating this into a full ecosystem-wide optimization. So in my study, I try to sort of fill this gap by answering 3 questions. The first is, how will Southern African and global green hydrogen and green ammonia demand evolve? What is the least cost way to scale the green hydrogen and green ammonia production and delivery infrastructure in the regions 2050? And how does that least cost configuration change with different learning rate, cost of capital, and demand scenarios? And so those scenarios are what you see here. Basically, I have an optimistic and pessimistic demand scenario, same thing with your learning rates or technology costs. And then I test all of that with different cost of capital assumptions. So that's just sort of setting the scene. So this is kind of the technical methodology. So essentially the way the optimization works is it was minimizing the total delivered cost of green hydrogen and green ammonia between 2020 and 2050. A couple of sort of key inputs there. Essentially what the model's doing is it takes a set of input demand nodes or locations which will require green hydrogen or green ammonia. It takes an input set of potential supply nodes, so potential supply sites, and then it optimizes the matching of those, tells you how much capacity you need to build at each of those supply nodes, and it does that over the full period. And it does that for a couple of use cases, green hydrogen for steel, as well as green ammonia for fertilizer production, for marine fuel production, and then green ammonia for export. I had to limit, there are more use cases, of course. South Africa's got a big synthetic fuels industry, but it was an MSc dissertation. So I'll quickly take you through sort of the inputs. The first is, the demand outlooks that I used. So how do you actually set how much is going to be required when the model's doing the optimization? The second is, so that's looking at locally, then globally, what are the demand outlooks I'll feed into the optimization? Third, which supply locations are being considered by the optimization model? And then thirdly, what are the sort of technology learning rate assumptions that were put into this? These graphs came out rough, sorry about that. So this is looking at the local demand outlooks. So you'll see there's a pretty broad range. Essentially, what I'm doing here is I had a sort of outlook in terms of final product. So in the case of steel, that's an outlook in terms of how much steel would be produced. I then multiply that by a green hydrogen penetration rate, and that's how you get this final number. The penetration rate, I kept the same between the pessimistic and optimistic scenarios because both of those scenarios are net zero by 2050 scenarios. But what's changing is the amount of steel that would be produced. So in the optimistic case, basically saying there's a revival of the South African steel industry, all capacity which is currently underutilized becomes fully utilized, and you see a growth in line with the IES or global steel production projection. The pessimistic one is essentially saying business as usual, we continue to see a structural decline. The same thing when you're looking at your marine and fertilizer application there. This is the global projection. So here you'll see basically the green hub scenario is an optimistic one, and then the net zero base is sort of the pessimistic one. Here I was only looking at green ammonia demand from countries which have announced import targets. So those are the UK, Germany, Korea, and Japan. That might have changed by now. And I assume that South Africa and Namibia captured a certain percent. So for the UK and Germany, I said 5%, or South Korea and Japan, I said 2.5%. A bunch of sort of reasoning behind that, which I won't get into now, but we can get into in the questions. Then it came to where do I actually locate this demand? So this is basically mapped according to current demand in the region. So this is where steel production happens in South Africa, none in Namibia. That's where marine bunkering fuel is produced, none in Namibia again. And that's where nitrogen fertilizer is produced, again, none in Namibia. That's the global picture in terms of those importers I mentioned. Then in terms of, telling the model these are where you can supply from, those supply nodes were basically included for one of three reasons. Either they were already listed as prioritized projects by the South African or Namibian governments, or they are basically just available locations near the demand centers. So that's used to essentially simulate on-site supply. So you have your end user and then you set up production right next to it essentially, or within 10 kilometers. And then the third reason was basically, if I noticed there was a particular location which had exquisite renewables potential, which is this GIS sort of raster calculation you can see here, then I popped a potential supply node there just to see what happened. Then I had to think about what are the potential ways that the model could match the supply and demand nodes. Does it transmit electricity over long distances? Or does it pipe molecules? And so here, basically, there are two options. So the model can either co-locate everything. Well, not quite everything. Essentially, you'd have your renewables production, you'd have your hydrogen or ammonia synthesis on the site of renewables production, and then you'd pipe the molecules to the end user. Or the second option is you'd have your renewables off-site, you transmit the electricity into the synthesis asset, so the thing that produces the hydrogen or ammonia, and that would be located at the end user. So essentially, do you go with pipeline or electricity transmission over distance? This here, I'm not going to talk too much about it. These are basically the learning rates. You'll be very familiar with these. I used NROL benchmarks as kind of the 2022 starting point. The optimistic sort of learning rates were taken from the paper by Wei et al. That was a paper done here where they basically tried to correct all the errors that you see from NROL and IEA learning rates. They always underestimate them. But for the pessimistic one, I used one of those NROL learning rates, which are generally sort of underestimates. Here, I won't spend too much time again. Basically, when it came to estimating the delivery cost, I built a couple of functions, basically, plotting the cost of delivery for your different technologies, hydrogen pipeline, ammonia pipeline, electricity transmission, based on the distance as well as the throughput, so the volume. And that was based on literature, and then I sort of polynomial interpolated that to create a function. So this is where it potentially gets interesting. So the actual results themselves. This here is basically a summary of how the supply and demand nodes were matched. And the key thing I want to point out here is that in over 70% of the scenarios, the on-site supply node is the one that matches demand. So in other words, the optimization says you should, in most cases, just put your green hydrogen or green ammonia plant right where you're going to be using it. So right next to the steel facility or right next to the fertilizer production facility. There are exceptions that start emerging where you see some weird configurations where a plant 200 kilometers away feeds a demand node. But generally those only happen when you see really high costs of capital and higher volumes. The higher volume basically means that your delivery cost, your levelized delivery cost, is lower, and therefore it makes sense to transport things over long distances. When it comes to the export, basically it said the Southern African region should export all its green ammonia for international markets from one place in southern Namibia, where you have extremely strong renewable capacity factors. Oh, these graphs are going crazy. Okay, I'll try and extract the key insights. I think so. In terms of the green hydrogen production cost, key thing to point out here. So these are your different supply nodes. Your green hydrogen production cost varies quite a lot between different supply nodes, and a big reason for that is that for the steel application, which is what we're looking at here, the model was required to supply essentially a consistent amount every hour throughout the year. So storage played a really important role. So when you incorporate that, basically the storage adds an extra 20 to 25% to the cost of your green hydrogen production. it also means that the site that you're looking at becomes much more important, because it's not just about how good is your sort of average capacity factor over the year, it's also about how well sort of temporally does the production of renewable energy at that site align with that sort of consistent demand requirement. Another thing to point out, those are sort of the delivered costs across scenarios, so the optimal delivered costs, and you'll notice that the actual delivery cost, so the yellow part, is a very, very small proportion of the overall delivered cost. This is when we look at green ammonia for local applications. So what you'll notice here is that it's a much sort of smaller difference between the different sites, and that's because when it came to the green ammonia applications, you didn't have that consistent hourly requirement. And so that essentially meant that you didn't require as much storage, so you didn't have a significant storage cost, but also it means that the differences in capacity factors between different sites become a lot less important. So similar sort of thing in terms of delivered costs, or delivery costs, they tend to be very small because most of the supply and demand nodes in the optimization were co-located, as I mentioned before. The only exceptions to this, and I haven't talked about, the pipeline versus electricity transmission trade-off. Basically, the model says always go with pipelines, never do long-distance electricity transmission, except in cases where you're looking at fairly short distances, so under 150 kilometers, and you have very low volumes. So under 50 kilotons per annum of green ammonia, under 5 kilotons per annum of green hydrogen. But you only really see volumes that small pre-2030. So longer term, you pretty much always go with pipelines over long-distance electricity transmission. Okay, so this is for export. I think key message here is really, you can get really cheap supply from Namibia in particular. It's world-class in terms of the cost of, delivered green ammonia to export markets. Here, your delivery cost makes up a slightly more significant proportion, so around 10%. But yeah, I think that's sort of the key. This is really sort of the key output from the optimization, basically showing, this is kind of like your infrastructure map for the region between now and 2050 for your green hydrogen and green ammonia ecosystem. And really what I was trying to illustrate is, depending on how your cost of capital changes or your learning rate assumptions change, the topography of the optimal network changes quite significantly. So in sort of a best case, 4% cost of capital, high demand, high learning rates scenario, you see pretty much everything co-located. You don't see many long distance pipelines or any long distance transmission lines, which are your purple and red lines. But then if you keep everything else the same, you just turn up the average cost of capital to about 7%, suddenly you see longer pipelines starting to pop up. It makes more sense to connect sort of optimal renewable energy production regions with demand nodes. And then lastly, if you go sort of worst case scenarios, so super high average WACC around 11%, low demand, poor learning rates, you see a lot more of this kind of, longer distance electricity transmission from the coastline into sort of inland demand nodes. So yeah, really just illustrating how important it is to, get your financing right. And here, this is the point I make again. Sorry, I mean, you can barely tell what's going on here. But essentially, keeping everything in terms of demand volumes and learning rates the same, just by changing the cost of capital from 11 to 7 to 4%, your average delivered cost of green hydrogen goes from, about $4 per kilogram down to, under $2 per kilogram, just on the basis of how cheaply you're able to finance these projects. Same thing from sort of an delivery infrastructure perspective, keeping everything else equal. If you get an 11% average cost of capital, you require 1,500 kilometers of ammonia pipeline in an optimal system by 2050. If you drop that down to 4% average cost of capital, under 370 kilometers. So it completely changes the picture in terms of what you actually build. One last point. So this is looking at a sort of Inflation Reduction Act type of green ammonia production credit. Basically, the key point here being if we were to introduce that kind of incentive, like has been introduced in the US, suddenly green hydrogen and green ammonia becomes competitive with grey hydrogen and ammonia in South Africa by 2030 in the majority of cases. So definitely something to consider there. Let me see. Okay, so we're still fine for time. So I'll go through, these are kind of the key so whats of this presentation. So you can forget about all the terrible graphs and just remember this and you'll be all good. So the first key takeaway is that on-site production is generally king. You don't want to transmit energy over long distances when it comes to green hydrogen and green ammonia, at least in the Southern African region. And a lot of this just comes down to the fact that in the region there isn't a significant natural gas pipeline network already developed. And so there's not all that much to retrofit. So basically don't go about building huge new networks, just co-locate everything. The second key takeaway is that pipelines feed electricity. So when you do need to move energy over longer distances, in the South African case, pipelines are almost always more cost effective than your high voltage DC transmission across the optimized scenarios here. However, there are, of course, exceptions to that. As I mentioned, generally when you have short transmission distances, under 100 kilometers, combined with low volumes, so under 5 kilotons per annum for green hydrogen, under 50 kilotons per annum for green ammonia. The third is then relating to that last slide, so an Inflation Reduction Act style green hydrogen and green ammonia incentive would have a significant impact on this region. So essentially it would mean that green hydrogen and green ammonia reach cost parity with grey hydrogen and grey ammonia by 2030 in 50% and 66% of the optimized scenarios respectively. This would require significant spending, but actually the amount you'd have to spend for a production tax credit like that in South Africa is less than what is spent essentially subsidizing the local synthetic fuels industry. So take from that what you will. The fourth point is then around regional collaboration. As I mentioned in the strategy documents currently published in the region, very little consideration of this, but the southern Namibian supply sites are consistently the optimal supply sites to global markets, achieving between $290 to $350 per ton delivered for green ammonia in 2050. Even when you account for the cost of building a new port in order to facilitate this. And this could be a significant industry, you're looking at sort of $5 billion to $9 billion per year in export from southern Namibia. And this represents about the same investment requirement that you need to service all that local demand. So really significant in sort of the grand scale of things, and an indication that there should be a lot more regional coordination going on, leveraging South Africa's industrial capacity and blending that with Namibia's exceptional renewable energy potential. So with that, thank you very much. Looking forward to questions.
Okay, questions for Colin?
I have a question about one of your final results where you were talking about like the lower cost of capital.
Yeah.
So in the graph on the right, I think you said that like with lower cost of capital cases, that resulted in fewer kilometers of pipeline being built.
Yeah.
Could you like elaborate on why that's the case? Because that is not super intuitive to me.
Yeah. So I'd have to work this on my head a bit. I had to wrap my head around it a few times during the dissertation as well. It largely comes down to essentially the higher your cost of capital, the difference in production cost between different sites becomes larger. So in other words, what are you doing when you co-locate production and demand? You're essentially sacrificing an optimal renewable energy production cost to have a much smaller delivery cost, right? But when you have super high cost of capital, then suddenly getting a lot more out of each solar panel and each wind turbine becomes a lot more important. So in other words, at higher cost of capital, suddenly the LCOE advantage of placing your renewables optimally becomes significantly higher. and therefore it starts to trade off with the additional delivery cost. So there's kind of this exponential relationship. The higher your cost of capital, the more important the optimal placement of your renewables. Does that kind of make sense? So when I'm talking about optimal placement of renewables, I'm talking about just the cost of the electricity, not the total cost of the green hydrogen or green ammonia.
Yeah, so, okay. Yeah, that can
Yeah.
So, yeah, thank you very much. Fascinating stuff. Yeah, share on the graph, so can't see.
I showed that PDF.
Too clever. The fundamental premise of green ammonia to me always seemed its ability to ship at large distances.
Yes.
It's cheaper than anything else you've been doing. It has this geopolitical superpower that you don't have the problem that you have with pipelines or with HVDC lines, which is that you're going point to point between regimes you may or may not be in love with in a decade or so.
Yeah.
So for that reason, I was slightly surprised that co-location of generation and demand is such a strong feature, which is exactly the opposite is where it sort of comes into its own. Long distances temporarily totally detached. So I just wonder
So the co-location finding applies specifically within South Africa. And so they obviously went into geopolitical concern. It's all within the same country, right? But if you're looking globally, I think what you'd probably find, looking at the delivered cost results between Namibia and Germany, for example, that co-locating production of green ammonia in Germany with German demand hubs will be more expensive than shipping it from Namibia. So when you look at a global scale, co-location doesn't always make sense, but if you're looking particularly in countries that do have strong renewable resource, co-locating and sort of hyper co-location, we literally have supply and demand nodes within sort of 10 to 20 kilometers of each other, makes the most sense.
And by demand, you mean demand for green ammonia per se? Because I would have thought going electricity, hydrogen, ammonia, back to potentially electricity is quite a lofty cycle.
Yeah, so for the local demand of green ammonia, I was looking at green ammonia for fertilizer production. So you do need the ammonia in that case. And then I was also looking at green ammonia as a marine bunkering fuel. So again, it's actually, the person demanding it, the shipping company actually wants it in ammonia form. But using it as sort of an intermediary doesn't make a whole lot of sense. There might be a case for it when it comes to that long distance shipping, as you mentioned, reconverting it when it gets to Germany or the UK. But then you have to assess on-site production in Germany and the UK versus off-site from Namibia and shipping it.
Hello, thanks a lot for the talk. You've rightly mentioned that the downstream processes from green hydrogen or hydrogen in general, they require a constant feed, or consistent input flow. Now, as I've heard from quite a few people now, green hydrogen suffers currently from inconsistent, flow rate outputs because of the weather. The sun is not always there as constant as it could be. And you've mentioned something about storage of hydrogen. Now, this is a potential solution. Nevertheless, you also rightly mentioned it's very expensive. It could be very dangerous. So I was just wondering, firstly, the cost implications for, this, as in general. But secondly, also further scenarios such as maybe, for example, using a battery on the, post-electrolysis, which could be expensive, but as a scenario, or maybe supplementing the flow with, temporarily with, say, gray hydrogen or blue hydrogen or something. So I was wondering, your opinion.
So the battery question I can answer, at least in this study, that was included as an option in the optimization. So when the optimizer was actually going through and figuring out what is the optimal sizing of your wind, your solar, your electrolyzer, your harbor wash, etc., it could choose, do you store hydrogen or do you store electricity in a battery? And it always chose the hydrogen storage. So at least based on the learning rate assumptions from NREL and the way it I'll study, just store the hydrogen, don't try and, invest in batteries. On, mixing in gray or blue hydrogen, sure, I mean, that would be a decision that the demander would have to make. The demand nodes, basically they might have some kind of commercial arrangement downstream, that means people will only buy from them if they can guarantee all the hydrogen used in their production process is green, right? And there's a lot of like EU regulation about that, where there are certain thresholds set. You can use as much blue hydrogen as you want or mix that in up to a certain threshold, but past that's big no. So that's really a regulatory question, I think, in my mind. Yeah.
Can I ask a question about the electricity grids? You've just looked at them as being a point-to-point supporter of bringing low-cost renewable power to the production site. But is there a possibility of sharing the cost and benefit? Because if the grid stability improves, or it's possible to deliver power for other purposes, the cost could be shared. Whereas in the case of a hydrogen pipeline, I guess it's not so easily shared.
Yeah, I think that's a really interesting point. I mean, when I was building this model, essentially I was assuming all of the electricity transmission lines that you'd need would be new build, because the current South African grid is basically constrained, particularly in the regions where you have the highest renewable energy potential. But I think more conversations need to happen in that regard when it comes to planning of the national grid going forward, because essentially the sort of electricity monopoly in the country is looking purely at provision of electricity for current consumption, and they're not building in electricity transmission, sort of synergies, I suppose, with the green hydrogen economy. So you could rerun this model and basically tell it, oh, they're actually going to be transmission lines there, which you don't have to build from scratch. Perhaps you just need to, upgrade capacity slightly, and then maybe long distance electricity transmission wins out against pipelines from a cost perspective. Yeah.
Right. Okay. Well, thank you very much to Colin about their dissertations. So, as Phil said very quietly, but I said aloud, pizza's arrived. So we'll get the pizza unpacked, and then we've got some time for basically just some networking, but also some discussions.
In case anyone fancies coming to a seminar next week, looks like the speaker has dropped out, but in 2 weeks' time, we'll be hearing from Lucy Powell, who comes from University of Colorado Boulder, talking about efficient wind energy. So I think it's around design optimization. So I hope to see some of you there.
Right. Thank you very much. So thank you very much.
Your presentation was very long. Thank you.